Hey everybody, welcome back. Today we're going to be discussing parallel circuits. We spent the last little bit of time discussing series circuits. We're going to take a look at parallel circuits, which is the other type of more complex circuits that you guys need to know. And we're going to go through the rules for parallel circuits and discuss some problem solving for parallel circuits using our same verb tables that we learned before. All right, let's dive in and get started. Okay. So we're going to follow the same three steps that we did when we were analyzing series circuits. First, we're going to look at the current through a parallel circuit, and then we'll look at the voltage across each component in a parallel circuit, and then we'll look at the equivalent resistance and put it all together for all three parallel circuit rules. To remind you, this here is a parallel circuit because the current comes out of the battery and it has a choice to split between each one of these components here. Remember, a series circuit, it goes through each component before it heads back to the battery, but for here, the current splits off and goes through each one of these branches before getting back together and going back into the battery. So how does the current work for a parallel circuit? Don't forget about Kirchhoff's rules that we talked about a few videos ago. What he said was, at an electrical junction, the current has a choice to split. So if we have a total current coming out of the battery, then some of that current is going to go through resistor 1, some of that current is going to go through resistor 2, and some of that current is going to go through resistor 3. But whatever splits off here has to come back together at this junction here before it heads back to the battery, because charge cannot be created or destroyed. So whatever splits off has to come back all together. So how does the current work through each one of these branches? Well, we have our total current here coming out of the battery, and then we have I1 going through resistor 1, I2 going through resistor 2, and I3 going through resistor 3. These three currents can be different if the resistances are different. But something that has to be true for all parallel circuits is the total current coming out of the battery has to equal, because of these junctions, the sum of all three currents through each one of the branches. All right, so this is different from series circuits. What we said for series circuits is the current through each one of the components are the same. But for parallel circuits, the sum of the current through each one of the branches has to equal that total current coming out of the battery. So we reached our first rule for parallel circuits. The sum of the currents in each of the branches must equal the total current in a parallel circuit. So I put an ammeter here. Whatever this ammeter reads has to be the sum of these three currents in a parallel circuit. All right, that's rule number 1. Let's take a look at rule number 2. How does the voltage work for a parallel circuit? So we talked about the junction rule for analyzing current, how the total current going into a junction has to equal the current going out. But how does voltage work? Here we're going to be taking a look at Kirchhoff's loop rule. And to remind you, what the loop rule said is that the total voltage, total change in voltage around any closed loop has to be 0. Now for a series circuit, we only had one loop for the current to go through. But here, we have at least 3 different loops here. We have loop number 1, where we go across resistor 1 and come back. We have loop number 2, where we go across resistor 2, and loop number 3, where we go across resistor 3. So let's say hypothetically we have like a 12-volt source from our battery. Well, if we gain 12 volts here, that means we have to drop 12 volts in order for the loop rule to hold. If we gain 12 volts for the blue loop, loop number 2, we have to drop 12 volts here. If we gain 12 volts, we have to drop 12 volts across resistor 3. So based on the loop rule, the voltages across each one of these resistors have to be exactly the same. There we go. Come on back. All right. So as you can see, the series and the parallel circuits, they kind of switch their rules for voltage and current. Here, the voltage across each one of these resistors have to equal the total voltage from the source. Where in a series circuit, the total voltage was the sum of all the voltages dropped. Remember that all of these rules are on page 4 of the reference table. So for parallel circuits, the voltage of the source is going to be equal for each one of these resistors in the circuit based on the loop rule. The voltage across each branch of a parallel circuit must be the same. And that is rule number 2. When we're analyzing series circuits, we were interested in something called equivalent resistance. So how does the equivalent resistance of a parallel circuit work? To remind you, what the equivalent resistance is what is the total resistance of these 3 resistors here, this grouping. Another way to say that is if I switch these 3 parallel resistors for a single resistor, what would have to be the resistance of that resistor? This would have the value of the equivalent resistance of these 3 resistors here. So how can we figure out the equivalent resistance of a parallel connection? We're going to follow the same kind of steps that we're looking at with series circuits. First, we're going to start with one of the rules that we figured out early on. The total current coming out of the battery has to be equal to the sum of the 3 currents through each one of these resistors. Using this as a starting point, we're going to see if we can derive the equation for equivalent resistance of a parallel connection. But first, let's think about this intuitively. We kind of saw for a series connection where there was one after the other, we had an idea that by adding more and more resistors, we would increase the total resistance of the current. But look at this situation. The more resistors I add in a parallel connection, I'm adding a new branch for the current to go through. It's kind of like adding another lane on the highway. By adding more and more lanes for the current to go through, is that going to increase the total resistance of a parallel connection or decrease it? Okay, well, let's see. We'll kind of talk about it when we get towards the end. Okay, so recall Ohm's law. R is equal to V over I. Anywhere I see an I can switch it with a V over R by just rearranging Ohm's law. And we know that V across each one of the resistors is going to be the same, but the resistor itself, we can label it R1, R2. That'll be the current through each one of those resistors. Let's substitute in for each one of those terms. Okay, well, for the total current, we can say the total current is the voltage over the equivalent resistance. If we solve for this, we have our equivalent resistance for the circuit. So for I1, we substitute V over I, so it's V over, we substitute V over R, so it's V over R1, V over R2, V over R3, and we can add more and more branches for our parallel circuit. We're just adding more and more terms in our equation here. But remember, our very first rule said that each one of these V's are exactly the same. So I can have an infinite number of branches in my parallel circuit. All of these V's will still cancel out. So because all of the V's are exactly the same, we have our equation for the equivalent resistance of a parallel connection. This, as you can see, is a bit more complicated than our series connection. We have 1 over the equivalent resistance of a parallel connection is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now, it might not be clear right off the bat, but what this equation is telling us is that the equivalent resistance decreases for each new branch of the circuit. Like I was saying before, if you add more and more lanes on the highway, more and more choices for that current to go through, you're going to decrease the total resistance of this group of resistors. More and more resistors we add in parallel decreases the equivalent resistance of the circuit. Okay, that's different from our series connection. In our series connection, the more resistors we add, we increase the total resistance, but for a parallel connection, more and more branches you add decreases the equivalent resistance of the entire circuit. So if we're clever with our series and our parallel connections, we can get really any value of resistance that we want for our circuit to make sure each component of the circuit gets the correct voltage and the correct current to make sure we don't burn it out and that it works right. Okay, so I want you to take a close look at the equation, page 4 of the reference table, the 1 over Req equation. If you take a look at this parallel grouping of resistors, we want to find the equivalent resistance here for these 3 6-ohm resistors. Well, we can say the equivalent resistance is going to be 1 over 6 plus 1 over 6 plus 1 over 6. That's 3 over 6. But remember, it's 1 over the equivalent resistance is equal to 3 over 6. So by taking the inverse, we see that these grouping of 3 6-ohm resistors is the same as a 2-ohm resistor. Don't forget that you have to solve for Req equals. You can't just leave it as 1 over Req. That's why it's equal to 2 ohms. Here, if we have 3 9-ohm resistors, well, we take a look at our equation. 1 over Req is equal to 1 over 9 plus 1 over 9 plus 1 over 9. That's 3 over 9. But then flipping it around, we get 9 over 3. And that's our 3-ohm resistor here. Same thing here. 3 12-ohm resistors in parallel is the same as a single 4-ohm resistor. Notice that the equivalent resistance in a parallel connection is always going to be less than any of the individual resistors that we put in there. That's different from our series situation. All right, I want you to try this one on your own. Pause the video and seriously try to solve this out. What would be the equivalent resistance of this grouping, these of resistors? You gotta brush up on your fraction skills. Okay, pause the video, give it a shot. But 1 over 5 plus 1 over 7 plus 1 over 12, taking the inverse of that answer, 1 over the answer, the equivalent resistance of these 3 resistors should be 2.3 ohms. Again, the equivalent resistance for a parallel connection is going to be less than any one of the single resistors in the connection. You decrease the total resistance by putting more and more resistors in parallel, adding more lanes on the highway. Okay. And with that, we have our 3 rules for parallel circuits. We have the rule for our current. Total current in a parallel circuit is the sum of any of the currents through each one of the branches in the circuit. The total voltage across each component in a parallel circuit is exactly the same. So the voltage across R1, voltage across R2 is always going to be equal to the voltage of the source, because we have a bunch of different closed loops. And to find the equivalent resistance, we have to use this more complicated equation here. 1 over Req is 1 over R1 plus 1 over R2 plus 1 over R3, and so on, depending on how many branches depending on how many branches we have in our parallel circuit. All of these equations are on page 4 of the reference table. All right, so what we're going to be doing next is we're going to be applying these 3 rules to analyzing particular parallel circuits. We're still going to be filling out our VERP table. We're going to be doing it by following these rules instead as compared to the series circuit rules. So we're going to move over to the whiteboard and we will be doing that now. All right, welcome to the whiteboard. We're going to analyze 2 different parallel circuits using our VERP table and the rules that we just learned over on the TV. So if you remember, when we did our series circuit, we had a 12-volt source with 3 2-kilo-ohm resistors. We're going to do that same example, but now we're going to have our 12-volt source, the 3 2-kilo-ohm resistors, but now they're going to be connected in parallel as opposed to be connected in series as before. I want you to compare what we do here to what we did in the series circuit video and see how the answers are a bit different. All right, so we're going to take a look at our VERP table. We use the VERP table to keep track of everything for series and parallel circuits. I highly recommend to draw out your VERP table for every parallel or series circuit that we give you. By using the vert table, it'll help you identify exactly which quantity you want and how exactly to get to the answers that we're interested in. For this example, I'm going to fully fill out the vert table. Remember that V is voltage, I is current, R is resistance, and P is power. R1, I always identify as the one closest to the battery. R2 is here, and R3 is here. And then here is the total of the entire circuit. This is where we put the equivalent resistance, the total voltage, and the total current, total power for the whole circuit. All right, so let's fill this out. First thing we do for our vert table is we identify what information is given to us, and then we go from there. Well, the total voltage that's supplied to this circuit is 12 volts. Put that here. And each resistor here is 2 kiloohms. Remember, kilo, that prefix means 1,000. So R1 is 2,000 ohms. R2 is 2,000 ohms. R3 is 2,000 ohms. Okay. All right, so now we're going to want to go through and figure out each one of the electrical specifications for this particular circuit. Okay, now based on the voltage rule for parallel circuits, the total voltage supplied to the circuit is going to be equal to the voltage across each one of these components. There's a bunch of different closed loops here. So if the total voltage is 12, that means the voltage across this resistor is 12, the voltage across this resistor is 12, and the voltage across this resistor is 12. So all of these are going to be 12. That's different from our series connection. Okay. Now, let's figure out the current through each one of these resistors. Well, if you remember from our vert table, as long as we have the V and the R, we can figure out the I, and we can figure out the P. But first, let's figure out the current through each one of these resistors here. Let's take a look at R1. We know the voltage across R1, and we know the resistance of R1. We can figure out the total current going through R1 here. So R is equal to V over I. R is 2,000 ohms. The voltage across R1 is 12 volts. We want to figure out how much current is going through. And the total current going through is equal to, work this out on your calculator. You're going to flip these. You're going to do 12 over 2,000 ends up being 0.006 amps. That's the same thing as saying 6 milliamps. There we go. So now, we would normally have to do the same calculation for each one of the resistors, but because they each have the same value for this particular circuit, it would be the same steps for each one of the resistors. So the current through each one is going to be 6 milliamps. All right, keep in mind that doesn't always hold for every parallel circuit I give you. The only reason why it's true here is because each one has the same value. But if each resistor had a different value, then the current through each one of the branches would be different. So make sure you keep that in mind. So we now know the current going through each one of the branches. But based on our current relationship for parallel circuits, the total current is the sum of each individual current going through each one of the branches. So we could use our current relationship to figure out the total current here on the bottom. So looking at the first relationship there, we can say the total current is equal to I1 plus I2 plus I3. If there was a fourth branch, we would put I4. If there was a fifth branch, we put I5. If there's only two branches, we would only do 1 and 2. But here, because there's 3 different branches, we have 3 different currents. Well, we know each one is 6 milliamps. 0.006 amps plus 0.006 amps plus. Okay, that's 6 milliamps, 6 milliamps, 6 milliamps. That is going to be 18 milliamps. Pretty standard for tabletop electronics. The total current going through this entire circuit is going to be. So let's think about what this means for a second. That means if I put an ammeter here or here, really anywhere on this side of the circuit, putting an ammeter anywhere around here will tell us the total current going through the entire circuit. That would be 18 milliamps. And that 18 milliamps splits. 6 milliamps go over here, 6 go here, and 6 go here. It's important to remember. The total current through each one of the branches, putting them all together, the sum will equal to the total current coming through the battery. All right. Now, to figure out the total resistance of a parallel connection, we actually have 2 options here. This is the beauty of a VERP table. By taking a look at our table, we see that we have 2 ways to figure out the equivalent resistance of this parallel connection. The easier way, if we look down the total row, we see that we have the voltage and the current. If we have the voltage and the current, we can figure out the resistance by using Ohm's law. A little more of a complicated way, but still a valid way to figure out the answer, is because we know the resistances of all 3 resistors, we can use this bottom relationship here, 1 over Req. For this video, I'm going to solve it both ways, and I want you to solve it out with me, and you'll see that no matter which way I pick, we're going to get the same answer for the equivalent resistance of this parallel connection. Gonna erase. Okay. So, let's start with the more complicated way. I want the equivalent resistance, the total resistance of these grouping of resistors here. So, filling out this row, I'm going to use the relationship that's given here first. 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Be very careful working these out. You know how to handle these fractions, but a common mistake that most people make is they analyze this side and then they stop. They don't actually solve for Req, they solve for 1 over Req. So we're going to make sure we take every step here. Our goal is the equivalent resistance. Let's plug in what we know. This is 1 over 2,000 plus 1 over 2,000. Make sure we put our units in. Units are ohms. Perfect. Okay, hope you can see. So 1 over the equivalent resistance is 1 over 2,000 plus 1 over 2,000 plus 1 over 2,000. So that's going to be 3 over 2,000, common denominator. Okay, so we can do here now, our goal is to find Req. So you could either cross multiply, or we could just flip both sides of the equation. We can say that Req is equal to 2,000 over 3. And taking 2,000 dividing by 3, you're going to see it's 666.66666 repeating. So I'm just going to call it 667. That's the total resistance of this connection. 667 ohms. Remember what I told you over at the TV? The equivalent resistance for a parallel connection is always going to be less than any one of the individual resistors. That's always a good way to check. If we're doing a parallel circuit and the equivalent resistance ends up higher than any of these, we know we made a mistake. The equivalent resistance has to be less because we're opening up more lanes on the highway, which will ease the resistance, easing our current traffic. All right, I'm going to do this same calculation, but I'm going to use Ohm's law this time. And like I said, by using our VERP table, we can see the easiest, quickest way to get to the answer. I hope you had that down. I'll erase it. If I was doing this problem, I would use Ohm's law. But I wanted to show you the other way to calculate it as well. So remember Ohm's law, we're going to verify this answer here. R is equal to V over I. Well, what R are we talking about? What V are we talking about? What I are we talking about? We're down the total row. So we want total, and REQ. Whenever you're using Ohm's law, you're picking the row that you're working in. Okay, well, REQ, the total resistance is 12 volts. Total current, 12 divided by 0.18 is going to be, you guessed it, 667 ohms. Everything works out. No matter which way you choose to get to the answer, you should always get the same answer because of the laws of physics. All right, I'm going to erase this. All right, what about the power? Well, we can use any one of the power relationships in order to get the power dissipated by each one of these resistors. Remember, the power dissipated is how much energy it's using every second, right? Joules per second is watts. So use any one of these. P is equal to V times I. Or P is equal to I squared R. Or P is equal to V squared over R. Check my answers here. I'm not going to work it out because we've done these before. But for every row, plug in the voltage, multiply it by the current, you're going to get the power. Or you can take the current squared times the R, or V squared over R. Any of these are going to get you to the answer. Do that now. Make sure it works out. But what I found for each one, I have 72 milliwatts for R1. Same for R2 because the value is the same. 0.72. And then the total, 0.216. And that's by using those power relationships there. Okay. Now, notice here, the current is the same through each one of these branches because the resistors are the same. If I change the value, these might not be exactly the same. But in every parallel circuit, no matter what, if I add up these three, I'm going to get the total current of the circuit. Same thing for the power. Notice the power dissipated by each one of these resistors is exactly the same. That's because the value is the same. If I change the value, I'm going to get different power. But something that's interesting is if we add up all of these, we'll get to the total power dissipated by the circuit. Now, to be honest with you, for most Regents questions, they usually only focus on V, I, or R, voltage, current, or resistance for anything here. But they have, and they could ask about the power dissipated. That's why we have the P column in our table. All right, that's our first example. We're going to do one more example before I end this video, and then we will be good for today. All right, hang tight for 1 second. All right, welcome back. Let's try this last example, and then we'll wrap it up for now. This was a Regents problem given one year. What they did was they provided this circuit here on the left. Notice we have two resistors connected in parallel. the very first step you want to do for analyzing any circuit is identify whether it's a series circuit or a parallel circuit. Here we see that we're in parallel because we have options for our current to flow through. We have two ammeters. We have ammeter 1 connected along this branch. We have ammeter 2 connected near the battery. The reading on ammeter 2 is 5 amps. This resistor here is given to be 3 ohms. This resistor is unknown. We have another 12 volt source here. And our goal is to figure out these three values. We want to find the equivalent resistance of the entire circuit. We want to find the reading on ammeter 1. And we want to find the value of this resistor. Okay. So, where I always start by analyzing circuits is I draw my VERP table and I see which cell do I want to figure out the answers here. Well, if I want REQ, that's the total resistance. So if I can fill in this cell, I have part A. The reading on ammeter 1. Remember, ammeters measure current. So I want to find the current through this branch, and that's the current through our 3 ohm resistor, which we can call R1. So we're going to find this cell here, that's part B. And finally, part C is the value of this resistor. It's not given, it's a mystery resistor. So we want to find this cell here. Okay, as soon as we fill in those cells, we're done with this problem. For the sake of educational purposes, I'm going to fill out the entire VERP table, but you're done once you fill in these 3 cells. Okay, so very first place to start, let's fill in the given information into this particular table. Well, the total voltage is given to be 12 volts. The value of resistor 1 is given to be 3 ohms. And in this ammeter, we see we have a reading of 5 amps. This ammeter is not along any one of the branches. It's closest to the battery. So this is the total current of our entire circuit. Notice that A1 is only along this branch. That's the current going through R1. If there was an ammeter here, 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 then that would be the current flowing through R2. By putting an ammeter anywhere here, we can see that the current splits off, and no matter any spot I pick on this edge here, we'll see that'll be the current going through that far resistor too. Always make sure we understand what we're looking at when we're filling in our table. Okay, next step, based on our voltage relationship, we can see that the voltage across any of these components is going to be the same, 12 volts. Fill that in. Now, finally, we can start looking to see what can we solve based on this given information. Well, we want to find the equivalent resistance, and by looking down this row, I see that we know the voltage and the current. We can use Ohm's law to figure out this last cell here, well, the REQ cell. So, Ohm's law says that the equivalent resistance is equal to V total over I total. I'm always looking down the row when it comes to Ohm's law. If I was looking at R2, I would say V2 over I2 is equal to R2. But we're looking at the total row. We want REQ. Nice and low, out of the way. 12 volts over a total current of 5 amps. And with that, the equivalent resistance is 12 divided by 5, 2.4 ohms. Let's plug that in, and that is the answer to part 1. 2.4, don't forget your units of ohms. Let's check here. We know for parallel circuits that the equivalent resistance has to be less than each one of these resistors. We're definitely less than 3. We'll have to double check and see when we figure out the value of resistor 2 that this make sure has to be less than that one. All right, that's part A. So for part B, we want to figure out the So for part B, we want to figure out the current going through the 3 ohm resistor. Once we figure that out, we have part B done, and we have another cell in our vert table. So as we can see, we have the voltage, we have the resistance. We can figure out the current, again, by Ohm's law. This is A. For part B, we have R1 is equal to V1 over I1. Whenever we're using Ohm's law, we're looking across our vert table. The voltage across is 12 volts. We filled that in. Okay. So the value of R1 is given to be 3 ohms. The voltage across, we filled that in already, is 12 volts. And we want to find the current. Okay. So figuring it out using our algebra, we get the current through I1 through branch 1 is going to be equal to 4 amps. 12 divided by 3 is 4. Fill it in. Boom. Okay. Now, by using our vert table and some logic, we can see that we can fill in this cell here. They're not exactly interested in this particular cell, so we don't really have to show our work. We know that the sum of each one of the currents is going to equal to the total current. So the total is 5, this one's 4, this cell here has to be 1. That tells us the current through this branch. There's 1 amp going here, 4 amps going here, equaling to a total of 5 amps. And finally, we want to figure out the resistance of this resistor. Because we know this, there's an easy way to get there. We know that this resistance is equal to this voltage over this current. We expect this to be 12 ohms. But I'm going to show the work using the complicated formula here to make sure we know how to use this formula, because you will be expected to know how to use it. And checking our answer based on Ohm's law, V over I. Let's try it out. I'm erasing. Okay. So for part C, 1 over Req is equal to 1 over R1 plus 1 over R2. Remember, we used Ohm's law over there, which is valid. R is equal to 12 volts over 1 amp, so this should be equal to 12 ohms. We're checking our work with the more complicated equation, making sure we know how to use this here. Okay. Well, the equivalent resistance we found already is 2.4 ohms is equal to 1 over 3 ohms plus 1 over R. That's R2. We want to find this value for this resistor. Okay, let's solve. What I could do is I could subtract over 1 over 3 and see that 1 over R is equal to 1 over 2.4 minus 2.4 ohms, minus 1 over 3 ohms. Okay, well, we have to make these denominators common. I can see that a factor that's common between these two is 24. If I multiply this by 10, I get 24. If I multiply this by 8, I get 24. So, hopefully you can still see it down here. 1 over r is equal to 10 over 24 ohms minus 8 over 24 ohms. Now, do you have to do this each step mathematically? Technically, no, you can just plug it into your calculator, but I want to make sure that we could work this out in case we don't have a calculator. Handy. 10 minus 8 is 2 over 24 ohms. So here's the relationship we have right now. 1 over r is equal to 2 over 24. You could cross multiply, or we could just flip everything and say r is equal to 24 ohms over 2. And with that, the correct answer is 12 ohms. Isn't that nice? We verified. We see that this resistor has to have a resistance of 12 ohms. Okay. So, we're done. We've answered all of the parts of the question. I'm going to quickly fill out the power column to make sure that we know how to do that. You can use any one of the power relationships that were given. I'm going to erase. Remember, P is equal to V times I is equal to I squared R. Pick your favorite. I'm just going to use V times I all the way across for each one. 12 times 4 is 48. And our unit is watts. 12 times 1 is 12. Unit is watts. 12 times 5 is 60 watts. And that is everything that they could possibly ask us about this circuit. We know the voltage across each one of the resistors. We know the current through each one of the branches. We know the resistance of each one of the resistors and the total resistance of this grouping, the entire equivalent resistance of the circuit. We also know the power dissipated by each one of these components. How much energy is each component using every second? Okay, now that it's fully filled out, you can answer all the different questions they could ask. Again, you don't have to fully fill out the table, you just have to fill it out to the point where we answer each one of the quantities of interest. Okay, and with that, we are done for now. I hope everyone's doing well, and I'll see you in the next video.